Hi, my name is Aaron Feeling, and this is my lab report for Lab 3, Magnetic Field of a Bar Magnet. For the introduction, the purpose of this lab was to observe and better understand magnetic fields through visual representation, to visually observe the relationship between distance and magnetic field, and to use the distance dependence of magnetic fields in the Biot-Savart law to find the magnetic moment of a bar magnet. The fundamentals of this lab were using a bar magnet to model a magnetic dipole, using the Biot-Savart law, and using the distance dependence formula of a bar magnet, which are shown. The results of this lab were that the magnetic moment of the bar magnet was 2.21 amperes times meters squared, and n equals negative 2.50. For the assumptions and models, we assume that the bar magnet acted as a magnetic dipole in order to apply the Biot-Savart law. For the experiment itself, the system was the bar magnet while the surroundings were everything else, and the initial conditions were the bar magnet and the magnetometer on the phone. For the details of the experiment, I first found the location of the magnetometer on the phone by sliding the phone perpendicularly to the axis that the ruler was on, both vertically then horizontally, with the bar magnet on one end of the ruler, in order to see at which position of the phone relative to the magnet the strongest magnetic field was being read. I then placed a piece of tape at that location in order to pinpoint the exact location. Then we moved on to the main experiment. First, we had to orient the phone so that the x component of the magnetic field was 0, ensuring that the Earth's magnetic field did not interfere at all with our reading for the on-axis magnetic field of the bar magnet. Then the on-axis distance from the bar magnet to the magnetometer was found using the ruler for several different magnet field values. These values were then linearized by taking the natural log of each side and then graphed. For part 2 of the experiment, we found the off-axis magnetic field of the bar magnet. We did so by first finding the on-axis distance from the bar magnet to the phone such that the net magnetic field was 100 microteslas. Then we slid the phone in the vertical direction the same distance and recorded each component of the net magnetic field at this location. The y component of the magnetic field due to the bar magnet was found by subtracting the Earth's contribution to the y component of the magnetic field from the total y component of the magnetic field at this location. Observations that I made during the experiment were that when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. As the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases, and that the position of the phone matters in terms of ensuring that the magnetic field of the Earth doesn't interfere with our readings for the magnetic field of the bar magnet. Now moving on to the calculations, I found that the distance dependence equation of the graph was y equals negative 3.043x minus 14.633. As you can see by the linearized equation to the right, n is the slope of the graph, which was negative 3.043, and the natural log of k equaled negative 14.633, and from this I was able to find k to be 4.42 times 10 to the negative 7th. I then used the Biot-Savart law to find the magnetic dipole moment of the bar magnet. Using r equals 1 meter, I set the Biot-Savart law equal to the distance dependence formula, and I solved for mu, getting a value of 2.21 amperes times meters squared. Moving on to my Glowscript model, I was able to model the magnetic field of the bar magnet computationally. I first created a cylinder to represent the magnet at the origin, and recorded my value for mu, then defining a function for the magnetic field at any given point relative to the position of the magnet. I then created 6 observation locations, 2 of which being on axis to the bar magnet, and 4 of which being perpendicular to the axis that the bar magnet was on. At each of these locations, I created arrows representing the magnitude and direction of the magnetic field due to the bar magnet. As you can see, I also did this for the locations that were perpendicular to the bar magnet's axis. I then was able to create an arrow representing the magnitude and direction of a magnetic field 45 degrees off axis by using the distance that I found in the experiment as another observation location, and using my function for magnetic field to calculate the magnetic field at this point. As you can see, this was the Glowscript model after I ran my code, and these were the values for the magnetic field at each location. For the off-axis magnetic field, I found through the Glowscript model that theoretically should be 2.70 times 10 to the negative 5 teslas. However, my experimental off-axis field was 6.36 times 10 to the negative 5th teslas, which was about an 81% difference. And now for the discussion. For model discrepancies, in this lab there very likely were none, as a bar magnet's magnetic field typically very closely models that of a magnetic dipole, so in this case our choice model likely yielded very accurate results. For potential sources of error, the magnetometer on the phone may not have been found very precisely, with a potential significant margin of error skewing distance results from bar magnet to the magnetometer. Additionally, if the reading on the magnetometer did not match Earth's net magnetic field before the experiment began, that may have skewed the off-axis results for the bar magnet's magnetic field. If I hadn't oriented the experiment to compensate for the magnetic north, then my results would have likely been much less accurate, as the Earth's magnetic field would have interfered with my reading and skewed the results. I would have had to try to account for the Earth's magnetic field in some other way, such as, for example, subtracting it from the total magnetic field. If I were to stick 2 identical magnets together end to end and do the same experiment, my measurements likely would have roughly doubled, as the magnetic field at a location relative to the 2 bar magnets would have roughly doubled. I concluded that both the Biot-Savart law and distance distance dependence can be applied to bar magnets with accurate results. Bar magnets can be used to accurately model magnetic dipoles, and distance is an important factor to consider in determining the strength of a magnetic field. Thank you for watching.